In this video, we're going to talk about oxidation numbers. So in our introduction to redox reactions, we talked about electron transfer theory, and this idea works well for atoms and monoatomic ions, but it doesn't work so well when the redox reactions become more complex. So for these, we need to use oxidation numbers. So the oxidation number for an atom is the apparent charge that the atom would have in a molecular ion if the electron pairs in the covalent bonds belonged entirely to the more electronegative atom. So if we look at an example, so water, H2O, and here's the Lewis structure for water. So oxygen, when it's neutral, contains 6 valence electrons. And when it's in the compound water, it is sharing electrons with the hydrogen atoms in order to have a full and stable octet. Because oxygen is more electronegative than hydrogen, when we're figuring out the oxidation number, it also gets hydrogen's 2 electrons. So it now has 2 extra electrons and a parent net charge of -2. So this is called its oxidation number. So the oxidation number for oxygen is -2. And because the hydrogens have lost their electrons, 1 each, they have oxidation numbers of +1 because they have lost a negative electron. So oxidation numbers can be assigned to common atoms and ions. And so these are the rules that you'll follow for assigning oxidation numbers. So if you have an element, all the atoms in that element have an oxidation number of 0. So for example, you have sodium, just plain sodium, its oxidation number is 0. The chlorine atoms in Cl2 both have an oxidation number of 0. So in terms of hydrogen, in most compounds, like with water that we just looked at, the oxidation number for hydrogen is a +1. So water is one example, also the H in HCl is +1. The exception is when hydrogen is in a metal hydride, and then its oxidation number is -1. So an example, the hydrogen in lithium hydride is -1. Now if we look at oxygen, in most compounds, like in the water we just looked at, the oxidation number for oxygen is -2. So there's the example, the O in H2O is -2. The exception for oxygen are peroxides, which you're not going to come across very often at all. But the oxidation number for oxygen in peroxides is -1. So peroxide is H2O2. So those oxygens have an oxidation number of -1. And finally, any monatomic ions have an oxidation number the same as the charge on the ion. So a sodium ion is +1, and a sulfur ion is -2. And so if those elements are in a compound as an ion, they would get an oxidation number equal to their charge. So once you have assigned the common oxidation numbers, the oxidation numbers of the other atoms in the compounds can be determined algebraically, because the sum of the oxidation numbers in a compound must equal 0, and the sum of the oxidation numbers in a polyatomic ion must equal the charge on the ion. So let's look at some examples to understand what that means. So in our first example, this is methane, CH4. So we need to figure out what the oxidation numbers are for both the C and the H in CH4. And we know that because this is a neutral molecule, that when we add the oxidation numbers together, they need to equal 0. So 1 carbon plus 4 hydrogens is going to have to equal 0. So hydrogen is assigned an oxidation number of +1. So carbon plus 4 ones is got to equal 0. right? So we know that carbon must be a -4 in order for overall the compound to equal 0. So we can write that this way. So here's CH4, C has an oxidation number of -4, and H an oxidation number of +1. So our next example is a polyatomic ion, MnO4, with a -1 charge. So in this case, the oxidation number for manganese plus 4 oxygens is going to have to equal -1, because that's the charge on the ion. Oxygen's assigned an oxidation number of -2, so we can put that information in. So Mn plus 4 -2s has to equal -1, right? So Mn minus 8 has to equal -1. Move the 8 over and add it, and we figure out that Mn has got to be +7 in order for this to work out. So here's the ion, MnO4 -1. The manganese has an oxidation number of +7, and the oxygen has an oxidation number of -2. One more example, Na2SO4. So this is a neutral molecule, so all the oxidation numbers are going to have to equal to 0. So we've got 2 sodiums plus a sulfur plus 4 oxygens. So we know that oxygen gets an oxidation number of -2. And sodium in there is an ion, right? This is a sodium ion with a sulfate ion. So it gets an oxidation number equal to its charge, which is +1. So we plug those numbers in, 2 times +1 plus the S, that's our unknown, plus 4 times -2 has to equal 0. So 2 plus S minus 8 has to equal 0. S minus 6 has to equal 0, which means that S is +6. So we can write that here. So the oxidation number of sodium is +1, the oxidation number of sulfur +6, and the oxidation number of oxygen -2. So how does this apply to redox reactions? So if the oxidation number of an atom or an ion changes during a chemical reaction, then a redox reaction has occurred. When the oxidation number for something increases, then it has been oxidized. When the oxidation number decreases, then it's a reduction. If the oxidation numbers don't change, then the reaction is not a redox reaction. So let's look at an example. Identify the oxidation and reduction in the following reaction. So in order to do this, what you need to do is figure out the oxidation numbers for all of the elements in that reaction. So I'll write that out again. So methane, the first reactant there, is one we just did as an example. So we know that hydrogen has a +1 oxidation number, and that gives carbon a -4 oxidation number. The oxygen is in an element, so it gets 0. So then in carbon dioxide, we know that oxygen is -2, and so overall the carbon dioxide has to equal to 0, so that carbon must be a +4. And then in water, which we've looked at before, oxygen's a -2 and hydrogen's a +1. So now we compare the oxidation numbers. So you'll notice that carbon on the reactant side has an oxidation number of -4, and then on the product side is +4. So the oxidation number of carbon has increased, so carbon was oxidized. The oxidation number for hydrogen didn't change. But then if we look at oxygen, it has gone from a 0 to a -2. So the oxidation number of oxygen decreased, so oxygen was reduced. So here's a second sample where we want to identify if there's an oxidation and reduction in this reaction. So we need to figure out all the oxidation numbers. So for the first thing, KClO3, so we know that oxygen is a +2, And we know that that potassium has an oxidation number equal to its charge, which is +1. So then we know that all of it together has to equal to 0. So we've got 3 -2s. So that's -6, and +1, -5. So we need another +5 on the chlorine. Then on the product side, potassium has a +1 and chlorine has a -1. And then oxygen is in its elemental form, so is a 0. So now when we compare, so we see that potassium's oxidation number hasn't changed. Chlorine's oxidation number has decreased, so chlorine was reduced. And oxygen's oxidation number has increased, so the oxygen was oxidized. So that's how you can determine oxidation numbers and use them to figure out if a reduction in oxidation has occurred in a reaction.